All right, so question one. So group one, why don't you walk us through that?
So we use the net accumulation function, or the exact net accumulation function. And we said f of x equals the integral pi over 2 to x pt dt, or maybe it's supposed to be dx.
Do you have something you can share with us?
I don't, I'm on a different, I'm on my iPad, so I can't share my screen.
Oh, okay.
I don't know if maybe one of them can, but
that's okay. If you can, I'm going to sort
of kind of where I got stuck, but then it wants us to evaluate at pi and 2 pi. So for this one, it just wants, like, I don't know how to like explain this in words, but I like know.
That's okay. I'm rushing to sign on with my iPad so I can
Okay.
I can kind of write down what you're saying.
I got a quick question.
Go ahead, Jacob.
Are arc links going to be on the exam?
Yes, they are. All right, so problem one here. So the first question is asking for that function f, right? So just to remind everyone, I think we're all working with the same function, right? So p of x is equal to, is it 2 cosine x minus 1?
Yeah.
Okay.
Or plus 1, sorry.
The plus 1? Okay.
Yeah.
All right, so what is problem 1 part A asking for?
The exact net accumulation of the signed area.
So I want signed area. And you said you wrote an integral, right?
Yeah.
What does that integral look like?
It's from pi over 2 to x, I think.
Okay.
And then we just said p of x, or I guess p of t, I guess we're supposed to use.
Yeah, or just anything but x.
Yeah.
Okay.
Okay, and then we're supposed to interpret the values of f of pi and f of 2 pi.
Okay, so f of pi, yeah, just in words, what does that mean?
Well, it's just saying like, what is the area, or the signed area from pi to, or from pi over 2 to pi, the accumulation, the net accumulation of it.
Okay. So from x equals pi over 2 to x equals pi.
And then it's the same thing for f of 2 pi. It's just from pi over 2 to 2 pi. The signed area accumulation.
So yeah, this is, I mean, once you can interpret one, you can interpret the other.
Yeah.
So one question I have for you is this: is that integral going to work for that entire interval?
It'll just work until, well, isn't the interval from 0 to 2 pi, and then it's saying only pi over 2?
So I guess my question is this: so you have signed area, right?
Yeah.
So is that integral going to work for the entire, pi over 2 to 2 pi?
I don't think so.
Yeah, it actually will. So
it will?
I'm trying to trick you. So signed area, so think about what happens when the integral, so really, let's just do a rough sketch of what this curve looks like. 2 cosine x plus 1, so it starts at 3. Centers at 1, goes down to -1. So it sort of looks like that, right? So this area will be positive or negative?
Positive.
How about this one?
Negative.
And then this one will be positive again.
Yep.
But for signed area, I can deal with negative areas. In fact, I want the area below the x-axis to be negative.
Oh, okay.
So because of that, your single integral is totally fine.
Okay, good.
All right. So is there a part C for this one?
Yes. So this one, or we skip, actually, there's 1b. So it says, without graphing f, predict when it will have the highest and lowest values and for what intervals of x the function will be increasing and decreasing.
Okay. So let's talk about that.
So, yeah, this one I got confused on.
So we want to know when the area, so from pi over 2 or from 0?
It just says, well, I mean,
Okay, so
the question's on 0 to 2 pi.
oh yeah, so part B, without graphing f, predict when it will have its highest and lowest values. Oh, so this was actually C. Okay. So for B, yeah, we haven't graphed f yet, which is fine. So this sine or this cosine wave that we drew, we're trying to figure out when it's going to have the highest area. So this right here, this is actually the rate of change graph, right?
Yeah.
So where do you think the area is going to be the highest?
Wouldn't it be, so it becomes negative when it goes through the x-axis.
What becomes negative?
Like the rate of change, right?
Good. Right.
Okay. And then so it comes back up above the x-axis. So wouldn't it just be at 2 pi?
Yeah, so this right here, this will be when the area is going to be the highest.
Okay.
Where will it be the lowest?
Wouldn't it be at 0?
This is actually, I'm just going from pi over 2 to pi.
Oh, pi over 2.
Otherwise, I'd agree with you.
Okay. So I guess pi over 2?
So that all
Or
depends,
like,
right? If pi over 2 is right about here,
yeah.
this might be, but I would say this is probably
Oh, yeah, that's more what I meant.
where the area is lowest.
Yeah.
But I think that's kind of a tricky thing. Does anybody have any questions about what I'm saying there?
Yeah, I just kind of had a question about how you'd exactly find like the specific point because like it said without graphing it. I thought setting like maybe P of T equal to 0, but like we just really haven't gone over. I feel like something
Yeah,
like
so it didn't say without graphing P, it said without graphing F.
okay. Oh,
Yeah, so I mean, yeah,
Okay.
I'm basing that off of just the rate of change.
okay, gotcha.
I have a question. So like if we were looking at from, like over the entire domain, wouldn't your highest area then be right at, where it first crosses the x-axis, because then it starts to, decrease due to the
If we were starting
negative
from
part?
0,
Yeah.
if we were starting from 0, I'd agree with you. But really,
Okay, cool.
this one asks for pi over 2. So
Yeah,
that's
I was just like making sure my thought process
your
was
thought
right.
process is good. I think I actually don't know for sure. I just think it's definitely in doubt, right?
Yeah, for
If we were
sure.
starting
Thank you,
from
though.
if we were starting from 0, I think it'd be a lot more clear. All right. Is there anything left on number 1?
There is, but it looks like part C is just the same kind of thing. Define in 2 ways a function of g that gives the exact total accumulation of signed area starting from x equals 0, and then it says the first way using an integral, and then the second way in terms of the function f, not using integral.
Okay.
So wouldn't just part the first way using the integral be literally the same as number 1, but with g of x?
Yep, there's the integral you need to find that area.
Okay, and then I'm not sure, does it just want, for the second one, does it want like f of f of 0 minus some? I'm not sure exactly what it means for the second.
So let me kind of get you started here. Like you already said, what is f of 2 pi going to give you?
It'll give you the signed area between 2 pi and pi over 2.
Right. So f of 2 pi will give me most of that area, but then how do I get this using f?
Starting at 0.
Yeah. So I see f of 0 here in the chat, but what am I going to do with these two terms?
Subtract
I
them?
subtract.
Yes.
Because here's the thing, f of 0, what that's going to give me, it's the area accumulated from pi over 2 to 0,
Yeah.
which is going to be negative.
Oh, okay.
Because I'm accumulating backwards in x.
Yeah.
So because of that, I am going to subtract it to make sure it becomes positive.
Okay. And then there's just one more. Use function notation to express the area of the region below the x-axis that's within the domain of P.
Okay.
Does it just want to does it just want like P of something?
Well, P does not give the area.
Oh, right.
F does. So
F
you
does.
really have to find where these points are. Did you find those?
I didn't get to this point.
Okay. So I think another group did because they needed to find those points for their own. What are those two x values where I cross the x-axis?
Pi over 2 and
4 pi over 3.
I'm sorry, one more time?
2 pi over 3 and 4 pi over 3.
Right. So those points right here, that's 4 pi over 3. And this is 2 pi over 3. So I would just use my f again. F of 4 pi over 3 minus f of 2 pi over 3.
Okay.
Or you can integrate your function between 2 pi over 3 and 4 pi over 3.
Yeah, okay.
Either way.
And that's it for number 1.
Cool. Any questions on number 1 before we move on to number 2? All right, everyone, let's have number 2.
Okay. Could I possibly share my screen?
Yeah, let me just jump off.
See that?
Yes.
So the question is, define a function h that gives the exact accumulation of unsigned area between the curve of P and the x-axis starting from x equals 0 without using an absolute value. So we first start out with the function and graphing it. So we have the function, and just from this we can tell that we're going to need 3 integrals because we have one set of domain, a second set, and then a third set. So in order to do that, we have to find the domain. So we have to find where p of x equals 0. So you just set that to 0 and you get cosine x equals -1/2, and we get the points that we mentioned before, 2 pi over 3 right here and 4 pi over 3.
Good.
So then we have to have 3 integrals. So the first integral in this interval would be from 0 to x because we want to specify for any x pt from the original rate of change function dt if x is between 0 and 2 pi over 3. So that would get us this area. Then for the second integral, we would have it between 2 pi over 3 and x pt dt if x is between 2 pi over 3 and 4 pi over 3, but because it's below the x-axis, it's going to be a negative area, but to counteract that, because we want the unsigned area, we just put a negative sign in front of the integral. And for the third section, we put, oh that's wrong, that should be 4 pi.
There you go.
4 pi over 3 to x pt dt if x is between 4 pi over 3 and 2 pi.
So I admit I kind of pushed you guys a little on this one. Here's the good news that you do need 3 integrals to make this work. You absolutely do, because if you want unsigned area and I don't let you use the absolute value operator, you need to find a way to make that negative, area below the x-axis. You need to find a way to make that positive, and that's what that negative sign there does. So let's look at the piecewise function here, and I'm just going to annotate. I absolutely agree for the first part, so I'll just copy it. So from x to 0 of p of t dt for x between 0 and 2 pi over 3. But let's say I have an x value that's between 2 pi over 3 and x. So if I just use the middle piece of the function you've defined there, what area am I getting? So that middle piece is just going to give me the area below the x-axis there.
Mm-hmm.
So if I really want to go from 0 out to something,
Oh, because we want the accumulate. Okay.
so then basically what you're going to have is this piece here.
0.
Not from 0 to x, I'm sorry. In this second interval, I'm assuming that I went all the way through that interval. So I went from 0 to 2 pi over 3 of pi over t dt, and then minus the integral from 2 pi over 3 to x of pi over t dt. And that's for this interval, 2 pi over 3, which is less than x, which is less than or equal to 4 pi over 3. Does it make sense why I have to do that?
Yeah.
Okay. And then by that logic,
The third one you just have to add on to that.
yeah, the third one, basically just take all of them. So
Okay.
I want the integral from 0 to 2 pi over 3 of p over t dt minus the integral from 2 pi over 3 all the way to 4 pi over 3 of p over t dt plus the integral from 4 pi over 3 to some x. And that's on the interval from 4 pi over 3 to x all the way to 2 pi.
Cool. Makes sense.
Good work on that one.
Sorry, I have a question.
Go for it.
So okay, just going back to like what the screen that he shared. So you mentioned that for the second part, we're going to be taking the integral function from 0 to 2 pi over 3, and then we're going to subtract that from the function that was 2 pi over 3 to x.
Mhm.
Was that because so I don't understand why we're subtracting it. Is it because we want to find out from the beginning and we want to find out how much it is?
No, the reason you're subtracting is because for unsigned area, I don't want any areas to be negative. I want to treat all areas as if they're positive.
I see, because signed area can be positive, negative, and all,
Yeah.
but unsigned can only be positive.
Yeah, so if you integrate the part of that curve that's below the x-axis, it'll
Right.
come up negative. So I just use the negative to
I see.
flip it to positive.
Awesome. Thank you so much.
Thank you. All right, let's move on to question 3.
So I didn't I did it all on paper, so I don't have anything to share. But
That's fine. I'm going to go back to my iPad and I'll
right,
narrate
cool.
for you.
It's like I can like talk through it, but
All right, what is question 3?
so it says to rotate the graph of P around the x-axis. I'm gonna see when it's like its domain real fast.
Okay.
It says let x increase through delta x intervals to fill the empty shell with cylinders, and then to define the accumulated volume of the cylinders in the shell as a
Okay.
function of x. But I don't think I'm assuming it wants the whole thing,
Yeah.
from 0 to 2 pi.
So how do we find that volume?
You're gonna have to use an integral.
Cool. What does that integral look like?
So we have the rate function already given to us?
No, so you got to build that as well.
Well, I mean, like, I'm at the part, I can't remember the name of it right now, but it's the thing we've been working with, the 2
Yeah.
cosine x.
Yeah, 2 cosine x plus 1 is
Yeah,
that's the function that we're revolving around the
yeah, that's going to be a key piece of the rate function.
Yeah.
My bad. I'll try to be very careful with my language,
That
but
was good.
so since these cylinders are varying through delta x intervals as a function of x, after I drew it out, I decided that these cylinders would be, disks, but they're not stacked on top of each other. They're like kind of progressing sideways. So they're like vertical.
Yep.
And then after that, it's clear. I mean, I can see that, okay, if it's progressing through delta x, then that means that the height of the cylinder is going to be changing.
So as x changes, height changes.
Yes.
So does that mean, so it all comes down to what area, where what face is the volume being stacked onto? Is it one of the flat sides, so the base, or is it the curved, as Mark says, the lateral surface?
I was saying the base.
Yeah, it is the base. So
Yeah.
if we were to look at this thing head on, that would be a circle, right?
Yes.
All right. So I'm going to take over a little bit right here just because I really want to get to arc length because we haven't had much time to talk about it. So we're looking at a circle, which means we're looking at an area which is pi times radius squared. No inner radius to deal with this time. There's not going to be any holes in this thing. So we're just going to deal with that one outer radius. So now what we want to do is we're dealing with x. We want to find a way to write our rate in terms of x. Our radius. So our radius is actually pretty nice. Our radius is just the y value. So both these cylinders I drew here, these discs, that's a y value, that's a y value. That's going to be true no matter where I am on this curve. So really what I have is the area is going to be pi times 2 cosine x plus 1 squared. Any questions about that? That really is, that is the most important part of your trying to do a volume accumulation like this. All right, so from there to get the volume, let's say I want the volume for any x, it's going to be the integral, and I'll do from 0 to x of, I called it a of x. So I'll do a of t dt. Any questions there? All right, I'm going to hold you a few minutes after because I usually do because there's a quiz. Today there's not. Let's do problem 4. So let's talk about the arc length. Who's my group 4?
It was us.
Okay.
Okay, so the question is define S. Also, I rewrote this on paper, so you can write it for us.
Okay.
So the question is define S, the arc length of the graph of P as a function of X, and we got to express it through function notation when the graph of P is between 0 and 2 pi, which is above the x-axis. So this way we knew what the initial X was, and then 2 pi is our final X. So what we did was, we know that as last class, when we're trying to find out the rate of change of arc length, we are dealing with a equations such as square root of 1 plus, and then the function's name, in this case is P. So square root 1 plus P prime of X, and then all of that squared dx. So that has been discussed earlier. So we kind of just took notes from that class. And using that, we knew that for function notation, because it said define S, we just said S of X equals to P of 2 pi minus P of 0 because those are the X values. So that's what we guessed was our total length using function.
Okay, so your rate of change looks great.
Okay.
That is the rate of change of arc length.
Mhm.
So one key idea from pretty much this whole class so far is if you know the exact rate of change of something and you want to show all the little accumulations in it, the sum of all those accumulations,
Mhm.
what operation do you have to do?
Integral.
I got to do an integral.
Right.
So I'm going to go from 0 to some x.
Right.
So this is why I say this rate of change, once you have that, that's the most important thing.
Yeah.
Because from there, I can just integrate that,
Right.
not x. So that's my arc length integral right there.
Mhm. It mentioned like expressing using function notation. So we did do the integral, but the answer was in function notation.
Okay.
It's okay. Yeah.
Oh, yeah, you called it p of x, which,
Yeah, I don't know if that's correct, but that's
yeah,
fine.
so p is this right here is the graph of p of x,
I see. Okay.
which you're actually doing a lot with p of x before you can integrate to get arc length.
So would you say for function notation, we do r and then subscript s and then 2 pi minus r subscript 0?
So I think what you're saying is this, r of s of 2
Yeah.
pi minus r of s of 0.
Is that correct?
No, because you're just comparing rates there.
I see.
You're not comparing accumulations.
Oh, okay.
On the other hand, if you said this, s of 2 pi minus s of 0,
Oh, okay.
this is a good arc length.
Okay. Thank you.
Thank you. All right, guys, I've stolen 3 minutes of your day here. Any last minute questions for me before I let you go? All right, if there are no questions, guys, go ahead. I don't have a quiz or anything for you to turn in. I know who was here. I know who participated, so you'll get credit if you were here. If you have any more questions, come see me in office hours at 3:30. But good work, everyone. Thank you.
Thank you. Have a good day.
Thank you.
Thank you.